today. The QR code and the chat in the Slack channel has a link to evaluations for the end of the day. So there should be an evaluation for each day. Please do those. And if you have something like truly terrible to say, like don't do it, let me know, and then we'll fix it, and then go back and no, don't record that. Well, just kidding. No, but we really do need to have some kind of evaluation because we have to write a report at the end of every year to send to NIH, and our program officer wants to make sure that we're not just throwing a party here or something or boring the heck out of you. So please do that for us. It's really helpful. And we do use them to be not to be flip. We actually do use them to make the choices about what to include in the next period and so forth. So please, by all means, let us know what we could do better and what would be good to include and so forth, and we can do that. All right. The other thing in terms of, what was her name from Love Boat, to reveal my age? Sort of the, sort of party planning features. There are events happening tonight of some sort. Have we decided on what they are, or is the boat still open? We're going to do both. All right, so you can pick either. Well, there were 4 options on the. Okay, so if there are 2 things happening. If you want to go out and do some kind of partying tonight, one is to go to Ponysaurus, and play trivia, and the other is to go listen to jazz at the Blue Note, which is one of Durham's signature places. So if either of those sound like fun, go do that. If not, find a good friend that you want to go out and have a beer with, or go to sleep. So whatever you want to do, please.
Also, if you want to go to an activity and you do not have a ride, just message the TAs and we will sort that for you guys so we can carpool and if you're at the hotel, bring you home and take you there.
Perfect. So we've got activities, we've got travel, we got evaluations. What else am I missing in terms of party planning bits, please?
If you're a fellow or a speaker and you haven't filled out your forms yet, or you filled it out online and didn't tell me about it, please email me so I know, because I'm going to start sending out emails at least once a day starting tonight. If you don't want to get an email, fill it out.
Thank you. Awesome. All right. So the next strategy is, we've talked today about the morning, we're jumping levels. So we've talked a bit about ego networks this morning and centrality scores and things like that. Yesterday we're at the individual level, and we've talked about whole network bits. It turns out that part of what's interesting about networks is that they have this really nice meso-level structure. So there's these elements of the community that people are embedded in that are more than just their peers, but not as much as the entire network. And those things are often really important. Like kind of the jokes we made yesterday, if you remember going to high school and having the cool kids table versus the losers table, right? Those are groups, right? And so finding those groups and networks is something that we can do. And that's a way, there's a lot of different names for them. And the current name, like the name I grew up with, subgroups. We would talk about cohesive subgroups, and that's the sociological literature. But recently the world has focused and concealed on this idea of thinking about communities. And so a community is a set of people that is a subgroup of a network that we're trying to find. The flip side of this are roles. And so this is this discussion of positional ideas that we talked about, which is another type of collective group in a network, but they're not necessarily people that are tied directly to each other. So we're going to talk about the methods for going and finding these. We're going to try to give you some suggestions for the best method that you might use. So we're going to put a little horse race sort of bit out there for you to have a look at that. And then when I finish yammering, John's going to show you some actually how-to in terms of some of the R code to get to that. All right. Now, by all means, of course, as usual, interrupt me, ask questions. That works out well. So, this is the plan for today. We'll probably do the little coffee break there between, if I remember right on the schedule, coffee's in the middle of Moody. So we'll just stay somewhere between community detection and relational block models. We'll take a quick stand up and move around to get the lunch off of us and hopefully go get some more caffeine. So we're going to start by asking a little bit about what these conceptions of cohesion and collective groups are. So we tend to think about this notion of cohesion or cohesive groups as a collective property of a social system. And if you remember your Durkheim from your first social theory class, This is the idea of mechanical solidarity. It's a group of people that are like us, we think the way we are, and it sort of shapes our beliefs and practices. That's a classic mechanical solidarity idea, and your cohesive group is the thing that is. It used to be, back in the Pleistocene at some point, that would be your tribe, and that was all there was. But in large-scale modern industrial societies, we don't have a tribe, which is a city. We have a small set of groups that we sort of hang out with and do things with, and we more or less intersect with them. And we think about cohesive groups are important sociologically and for health reasons because our group we're in shapes the things that we deem as acceptable. And so we have this linkage between our cohesive embedded group that we're in and the mental model we have about what's appropriate in the world. And so those two things are said to go together. We tend to also think that there's this notion that if we have a strong cohesive feeling towards the world, that we're going to perform better. So if you think about these sort of archetypical, Bad News Bears kind of coach movies where they're down at halftime and the coach comes out and tells a great story about how good you should be, that kind of cohesive feeling then leads to success. Well, that's the idea, that if your social group is cohesive, then you feel good about it and you perform better. That's the kind of model. We're not going to do all of that today, so we're going to sort of not think about this recursive link so much because we don't have time to do that. Instead, we're going to just focus really on figuring out this relational component. So what is it about the pattern of ties that creates a cohesive group, and how might we measure it? Okay. So for me, this starts with a lot of the work that's coming out of Linton Freeman's work, which was built on some of the original structural functionalist work in social networks. And a cohesive group is built on the sociological concept of a clique. I like to think about it as really the intersection of these two dimensions. And so the most common dimension we tend to think about is this first one on the y-axis, which is the amount of connectivity in the network. And you think about a cohesive group as being one where there are lots of ties. So a dense social network is what we're interested in. But it's not just that. So it's not just that it's high connectivity. High connectivity leads to a certain kind of relational cohesion, but it doesn't necessarily lead to a distinctive community. Instead, you need to have some element of boundary salience. There has to be some distinction between an us versus a them, right? And so the distinction between us and them is what creates a boundary between communities as opposed to just a single overall network, right? So how do we go about measuring this? It turns out that traditionally there are lots of different ways to do this, and the early history focused on generalization of graph theoretical elements, and I'll give you some examples of what those look like. They're good ideas, sort of, mathematically about what a clique is, for example, but in practical real data analysis, they tend not to work very well. And then there was a set of groups of what I refer to as pattern detection approaches that came out of sort of trying to essentially take an idea from one sort of analysis and port it over to another. So the classic example is using factor analysis on relational data in order to identify groups, or to use hierarchical cluster analysis or something like this. A lot of these methods were reasonably ad hoc. They were people like you and I who were sitting down just trying to figure out the best way to do it, and we just tried shit until it worked, and if it worked good enough for us, we used it. Thankfully, I think we've gotten a little better than that. So we've sort of moved beyond the purely ad hoc models to something else, and we're going to talk a bit about those. So just to sort of narrow it down a bit what we're trying to do, if I give you a network and I say find me groups in the network, what you expect to find is something like this. There's some set of nodes that have lots of ties to each other, they're near each other in the social space, and thus that they have more ties with each other than you'd expect with anyone else. The historical version of this, like I said a minute ago, is this notion of a clique. And a clique in graph theory is a set of nodes for which each node has a tie to every other node. And so it has a complete density of 1. It has everyone's connected to n-1 alters. The distance between every pair is equal to 1. Right? All of these features come down to being exactly perfect, at their limit in a clique. And so there was a whole series of ideas that said, well, a clique is certainly a group. So if I have a clique, I have a group. That seems reasonable, especially as drawn here. And so I could take these properties and just relax them a little bit. So instead of a density of 1, let's take a density of 0.9. Or instead of a distance between every pair is 1, let's take a distance of everywhere by 1.2 or something, right? So just relax each of these a little bit and see if that would help you find reasonable groups and social networks. It turns out that it doesn't do a very good job. And the reason is that cliques, for example, overlap very heavily. And so if I try to find cliques in a network, then what I really find is that node 5 is in a couple different cliques, node 4 is in 3, node 3 is in 2. And so you end up with this thing that's true in the sense that you know what a clique is there, but it's not analytically useful. And so we could try other things like K-cores. Problem with K-cores is that they're often very fragile, so an addition of a single edge will change what that is. And there's this whole series in the history of group detection algorithms that try to relax the notion of a clique to find something that works. Again, as I say here, there are tools that find it, but I've never found a whole lot of practical use for it. So instead, we've gone with models that are more algorithmic sorting models. And what they try to do is to recast the problem just a little bit and say that I don't know much about the particular in-group pattern of ties necessarily, but what the key defining feature of a community in a network is that there's more volume on the diagonal of the mixing matrix than between the mixing matrix. That essentially each node or most of the nodes in the network have more ties with other members of the group than they have with anyone else in this set. And so that's a feature known. That's the feature that people typically try to optimize. Right, so we try to identify, so the problem, let me restate this because I'm blabbering. So what we try to do is sort nodes into communities such that the amount of volume in this diagonal is higher than you'd expect by any other option. Right, so that would be an optimal set of assignments of nodes to groups. So how do we do that? Well, first we need some actual measure of that feature, of that intuitive notion that there's more ties within group than between group. And then we need some algorithm, some process that would maximize that first thing. And so the measure of fit that the field has typically come to sort of use recently is this thing called the quality function or the modularity score. And we talked about this briefly when we were discussing homophily yesterday. And so this is the formula for modularity, and this formula has a set of features. The key element is that it's summing over over the adjacency matrix, the number of observed ties. We're subtracting from that some function of the expected number of ties. This is what's known as it's a configuration model. So it's the degree of I or the degree of j divided by the number of total edges. You don't have to have that particular expected model. There are other models that are out there, but that's a useful one for most of what we do. Then there's this pesky little thing called the resolution parameter. The resolution parameter tunes how much bigger than expected the tie has to be to count towards community quality. And this is an indicator of being in the same group. And so if you think about, I know a lot of people don't like looking at equations, but if you think about what this is trying to do, if everybody was in completely separate groups, then the only time you'd see a tie was when this was true, and that you would be subtracting out all of the noise that could be there, and so this thing would be perfect, and so you'd get a value of 1 out of this guy if it was the case that everyone was in their own separate group. If everyone is in a random group, then this thing goes to 0. So if this were equal to that, this thing goes to 0. It doesn't matter really where you're assigned, because at that point, then the whole thing goes to 0. And that's the relevant range that we're interested in. So a quality score of 0 indicates random mixing. A quality score of 1 would indicate that you have a perfect assignment of nodes to groups and no cross-group ties. In practice, of course, these scores are somewhat all over the place, and so you end up with a really sort of weak clustering would look something like this, and a modularity score of 0.2, a really strong clustering is a quality score of about 0.68. Peter Muka, who usually gives this talk during the thing, absolutely hates it when I say a good score is 0.6 or a bad score is 0.4, because in, of course, practice, what's a good and bad score depends entirely on what that expected value is, right? So not knowing that means that the score of comparing a 0.68 in one graph to a 0.68 in another graph is probably meaningless. Right? You don't really have a good sense of this. This isn't a metric in that kind of a sense. But as a general rule of thumb for trying to find groups, you're within any given network with a fixed volume and a fixed degree sequence, it's going to be the case that the higher the modularity, the more likely you're going to end up with a group that looks kind of like this cluster set as opposed to some other mess. Now, solving the community detection problem is hard, right? Intuitively, it makes sense what it is, but it turns out that the problem is that if you don't know ahead of time the number of groups in your community, there are lots of different combinatorials for assigning these things, right? And so I can assign, in this little graph here, it looks like I have 6 different communities that I assigned things to. I could have decided 5, I could have decided 7, I could have decided 20, right? So you have to decide not just how many groups there are, but what the optimal assignment of nodes to groups are that would give you this maximum density along the diagonal of the mixing matrix. And so this ends up being what's known as an NP-hard problem. It ends up being a problem that you can't solve by just enumerating the number of possible solutions. But if you would like to, there is a community, what's the name of I don't even list it in the notes because I'm afraid you might try it, but there is a version in iGraph that will let you do all possible assignments of nodes to groups to find the optimal solution. Don't use it on a graph bigger than about 6 nodes, right? Because it will take the rest of your life to converge. But you can do it if you really for people who really want to test methods on small sort of such situations. There's possibilities to do that. So because there is no sort of fixed solution to do this, what we have instead are a whole host of heuristics. And I joked yesterday that you make your sort of network chops in this field by inventing a centrality measure. The other way to make your network chops is to invent a clustering method. So you can either come up with a heuristic or a centrality score. One or the other will help you get to the point of where you can be famous in the field. So I'm going to walk through a few of these and then sort of give you a little advice on which ones to use. So the first branch of the solutions of the heuristic space are what I refer to as agglomerative methods. And so what these methods do, and here's a set of them, and we're going to talk about a couple of them in particular. But what these methods do is they say, let's take my network, and the process is involved where you first start by identifying sets of nodes that are clearly closely tied to each other. And then you add to those nodes nodes that are closely tied to them, and you keep doing this process until you find some set of nodes which would maximize this modularity. Now that process of sort of going from the bottom up works really well in most cases, and the fast greedy method does just that. That's exactly what it does. And it works really fast, and it's a nice, efficient method for doing it. The problem is that whenever you do that, if you make a mistake early, if you have a tie where you put 2 nodes together that should be in separate groups, you're just going to build on that mistake. So the Louvain method, or later the Leiden method, have come up with this proposal process where they start doing that, but then at each stage they back up a little bit and so revisit to see whether or not the assignment they made a couple stages ago is a good one or not. And so this process goes through and makes that kind of idea. Ken Frank, who's at Michigan State, his model does this. A tool I built did this. So it's a nice way of saying, look, I'm going to make a guess early, but then I'm going to go back and check later what's there. Now what about this pesky resolution parameter idea? The idea here is that this is a tuning parameter. It's kind of like a microscope idea. And as Peter's phrase is that every microscope needs a good knob. Well, this is the idea, that some things are in focus at one resolution and other things are in focus at another resolution. And the point is that social systems are rarely one community solution. And if you don't believe this is true, just imagine trying to cluster faculty members at a university. We're in departments, right? Departments tend to have subparts that they focus on. The departments are nested in schools. Schools are nested in the university. There's at least 4 good, reasonable levels that you could think of as the communities that faculty belong to, right? And so a different resolution parameter will give you each of those 4 communities. And so what you want to do is find some solution that is reasonably stable within a range of the resolution parameters. So in this particular graph, which I don't remember which one it is, but this particular graph that this thing was run on, the authors went through and they said, let's just try a bunch of different resolution parameters and figure out the number of communities that come out at each solution. And you see that there are 2 ranges of values for which the solutions are pretty stable. You find the same number of communities at either one, and both of those are fine, right? Neither one is a false retry. It's just one's going to be a big set, a large number of small groups, and the other is going to be a small number of big groups. And it's up to you to figure out which one is useful. Peter Muka and his team came up with a really nice solution to this problem in the general case, which is that it turns out that if you go through and you do this search process across the space of all possible partitions that are found that maximize modularity for any given resolution, they fall on the outside of this convex hull. And it turns out that what you think might be an infinite number of solutions, it's like, crap, Moody, now I got to find all these different solutions, are really a much smaller set than you think they are. Because in this case, any solution that falls on this outside hull is going to be optimal. And any solution that's the same color, that it turns out that falls on a linear segment of this line, are in fact the exact same solutions. The partitions will be identical. And so that means what you thought might be 100 solutions might actually be 10 solutions. And so actually looking at them and searching through them is not that hard to do. And so in this particular graph, what I'm showing is the modularity score non-normalized on the y-axis, and on the secondary y-axis, the number of communities that you find. And so here you can see that there's a nice stable solution at 9 communities at that resolution range, and another here. All right, so that's what that's showing. The opposite approach to agglomerative methods are divisive methods. And so here the idea is, I have this big network. Let's just break it apart at its weakest link. And so the classic example of this is the edge betweenness method that Newman and Gurman came up with. Newman and Gurvan, thank you, I got my syllables mixed up, came up with, which says we talked about betweenness centrality on nodes. Well, you can calculate betweenness for an edge as well. And an edge, it says essentially how much of all the geodesic weight in this graph between all pairs of nodes is being carried on this edge. You find the edge that has the highest betweenness centrality, remove that edge, this graph would break into 2 pieces. Go back, recalculate the betweenness centrality, it's probably going to be one of these 2 edges, delete them, and you get new clusters. So you can take the graph at its highest level and keep splitting it until it breaks up into pieces, and you're always breaking it at the weakest space, and by virtue of doing that, you're going to end up with, ideally, optimally modular communities. This method actually works very well on small, somewhat sparse graphs. Because it has to calculate edge betweenness each iteration of the set over again, it ends up being pretty slow. So it's not great for big, dense graphs, but it works really well for smaller graphs. There are other divisive methods, which I can talk about later if we have time, but that's the idea. Then there's a series of models that I refer to as process optimization methods, which is probably not a fair label, but I needed something. So the idea is that you can imagine that finding the exact community is hard to do, but I know that communities map on to social processes. So what I could do is simulate the social process, and then from that, the community should emerge. The classic example would be, say, let's imagine a peer influence model. If I think that communities are going to generate different belief structures, I can seed a bunch of random beliefs, let a peer influence model run, and people who hold different beliefs are probably in the same community as each other. So you can sort of think about a social process operating on the graph and then use that as a proxy for searching the graph directly. And that's what things like these do. So label propagation says, let's randomly drop some labels in the graph and then let the nodes that are tied to those labels take the mode of the nodes they're tied to and let the labels propagate through the graph. And at there's some tricks to it, but when that's done, you'll get subsets of the network that if they're tightly reconnected to each other, should end up having the same labels on them. And there's lots of different versions of this. There's an infomap version, there's a walk trap version. What walk trap does is it takes the same idea, but instead of looking at adjacent nodes, it does a random walk through the network, and the number of times you revisit the same nodes, the number of times a random walker gets trapped in a clique, for example, would be the idea that you end up being stuck there. All right. There are a couple of still direct search tools, so factions and negapy are some old sociological ones that are around. I'm not going to go into those in detail. There's a whole series of eigenvector-based methods. And the beauty of the eigenvector-based methods is that the math theory on eigenvectors is well known. We understand where these fit. If you've ever done a factor analysis or an SVD or something like that, then you'll see these methods. Like this is what you're used to doing. So if you're used to creating scales out of psychometric items, that's what an SVD is, or a QA, or so those kinds of models are. I'll talk a bit about how so the beauty of these models is they're very fast. They work on very large graphs. They tend to work reasonably well on well-clustered graphs, but you're going to see in a minute they don't work particularly well on complex graphs. Then there's a new set of methods that have come out really in the last 10 years, which are known as stochastic block models. And I hate the name of these because we're going to use block models in a different word later. So, but these are, because block models mean for sociologists something that's much more general than this kind of block model. But what a stochastic block model does is it says, let's imagine I'm trying to predict the likelihood of a tie between two nodes. And I'm going to posit some latent group out there, and if people who are members of the same group are more likely to be tied. And so it builds a generative model of the network as a function of the group assignments. And by virtue of having this generative model, you can then do really nice theoretical things with what the block model is. So from a statistical theory standpoint, this is by far the most rigorous model set that's out there. As you'll see, from a practical standpoint, you have to seed these things somewhere, right? And there are two things you have to do that these methods don't do particularly well, is you have to provide a seed solution to start with that you then adjust from, and then you have to provide some number of solutions, it's like number of clusters solution problem, both of which end up sort of undercutting the effectiveness in real graphs pretty effectively. So you might think, you might hope, of course, that if I give you 5 methods, please.
So you, in one of the stochastic methods, you listed the computation complexity of n log n, and then the eigenvector methods was like n squared and 3, I guess. Okay, so n squared and 3
Yeah.
here. But previously you had something like n log n. So why are they even like doing these eigenvector methods? Are these in some sense better than the stochastic approach you mentioned previously?
Yeah, the leading eigenvector solutions tend to be a little faster than the stochastic block model is, but as in practice, most of the stochastic block.
But what you had like a few slides before, you had this n log n. Yeah, here was n squared plus n. Yeah, this is the way you get it.
Yeah, so they're just very different processes, and so they're trying to get at the same spot, but they end up with different solutions.
So if this line method has like n log n,
Yeah.
when would you use this instead of like an eigenvector method, which is a bit more expensive?
Yeah, my answer would be you would always use the Leiden method over the eigenvector method. But in practice, people use the eigenvector method because they don't do a search first. And so it's easy for them to get, and they can just they can just sort on the first eigenvector and call it done. And so that ends up being, I think it's largely historical preference than anything else. But you're exactly right. And I'm hopefully going to answer that question next. So if you apply these different heuristics to the same graph, you get different answers, which is kind of depressing. Because what you would hope is that you would get the same answer, that it wouldn't matter what tool you use, you effectively find the same thing. And in fairness, if you have a really big, like giant graph that's really highly clustered, if you're gonna cluster something like the Wikipedia co-citation graph, it doesn't really matter. There's a million nodes, it's gonna differ a little bit on the edges. But for the kinds of things that sociologists care about, where we care whether or not these orange nodes are one community or 3 communities, it actually makes a difference. And the solution that you get out of these different models will be different. Now the score you see on the top here is the modularity score. And so you'll see that in this case, the Louvain method ended up with pretty close to the highest solution, 0.62. The fast greedy is also the same. And those methods are, just eyeballing them, they look pretty close to the same solution. It might be a slight different in there. One of the problems with modularity is that it's not unique. You can have the same modularity. You can have two graphs with the same highest modularity score in different solutions. That's because you can have nodes that are effectively has the same degrees or same proportion of in-group and out-group ties, and you could switch their places, and that would then create different solutions with the same modularity score. So if you go through all these different solutions, the 8 different solutions that I looked at, this is the number of time pairs of nodes are put in the same set. So you can see that there's pretty high agreement, for example, on these 5 nodes, pretty high agreement on these 5 nodes. Some nodes put these 2 with them, some do not, right? So there's a slight variance in the solutions that these happen. Now, those of you that have an algorithmic bug in you, you might look at this and go, well, there's your answer, right? Do this, and then apply it again, right? And that's actually, there's a wonderful little model out there. which does just that, where you take a bunch of different solutions, you put them into this model, then now you have a new weighted graph, apply all the solutions, get them again, do it again, and that'll give you a new set. It's called a consensus clustering of the graph, and a consensus clustering of graph can do a very nice job if you're patient. It's just really slow because you're doing all of those models across all the sets. But it takes all the advantages and disadvantages of these different heuristics. So which one should you use? Well, we wanted to think about this as a problem, so myself and Peter and Tom and a bunch of us have been working on this problem, Gabe. And what we did is we just said, let's do a classic Monte Carlo experiment. Let's set up a bunch of graphs where we know the answers and then figure out which one of these solutions actually recover the true answer most often. The problem with doing a Monte Carlo experiment in this kind of setting is that you can't really use a real life network because you don't know the truth, right? You don't know the answer. That's sort of the problem you have to start with. And simulated networks are typically too simple. Like they're just not complicated enough. So because I can't ever do anything simply, we created a bunch of really complicated networks that we think do a nice job of mapping onto some features that characterize social networks well, while still knowing what the true answer is, and then figuring out how to do that. And so these networks, we deal with 4 different topologies that we care about. And so the first one we're calling this double nested structure, and what that means is that all of the groups, we think that most social systems have hierarchically nested groups. And so the idea is that you have departments, you have colleges, you have universities. And so you have some set of, if you were to imagine a full partitioning of the network, you have at the finest level, you have communities. And communities are nested in groups, which are nested in crowds, which are nested in the entire population. And so we've set it up so that we have some set of, not only that, so we have a set of communities in each of these simulated structures, but we also have some nodes that are effectively noise, that we have a community that doesn't have an actual community structure. They're just noise put into the graph. And this is actually 2 versions, because essentially what I'm going to do at each sort of turn of the simulation is I'm going to make the strength of the diagonal a little stronger or a little weaker. So I'm going to increase the signal. And when I decrease the signal, when I make it less community, when I make it less modular, I'm either going to redistribute those same number of ties throughout the graph, or I'm just going to delete them. So that's the difference between these 2 sets. Otherwise, the main difference here is that in this case, some of the groups are really big and some of the groups are really small. And in this case, there's just a lot of noise, right? So there's a few real communities, but most of the communities are not real. We then go through, this is just to give you a little sense of what these things look like, right? And so, they're still not, you might have a sense of how these things are going to fail, but I'll explain it a little bit later. But you can see, for example, in these hidden communities, like there are a lot of noise here, but the things we want to find are these little communities in the set. Right? And then as we add, so these are the clearest, most modular versions, and these we have a whole lot of noise, right, in these sets. Maximization methods. They usually have a resolution parameter that we can change. In some of these modules, you have to decide the walk length, for example. So we did our best to try to come up with either to imagine a user who's picked up iGraph, opened the manual, and said cluster.Leiden, and see what kind of answer they get. And so that's what we're doing. Now, whenever we have a resolution parameter, we do this sweep process. So we go through and try to find the set that we can that's going to optimize the solution. And this is a little bit of unfairness, because we just do the sweep and we take the best fit. So it's assuming that you as a user would be able to do that. Now, what is the best fit? The best fit we're using is the RAND index, or the adjusted RAND index. And this is just the extent to which pairs of nodes are similarly classified. It's a partition agreement score. I can go through the details if you want, but it's effectively saying that if you and I are in the same group, and we should be in the same group, and we get a point in our favor. If we're in a different group and we're classified as in different groups, we get a point in our favor. So if the partition does what it's supposed to do, it matches nicely. So now you're going to see a bunch of different results for this, because the way we set up these networks is that it turns out that networks have, the networks we care about have a couple of other features in addition to just this mixing pattern. We can also think about the degree distribution of the network. So either is it an Erdos random kind of structure in which we're going to have effectively a Poisson distribution, or is it a really long-tailed distribution? So we've changed the degree distribution. And then we realized that part of what we care about for groups is that we expect that the dyadic feature should carry some information about the group. For example, we ought to see higher reciprocity rates within group than between groups. We ought to see more transitive closure within group than between group. So we can weight the graph by those features. And so we have an edge feature, which should be indicative of being in the same group or not. And so we have binary or weighted, and we have this skew distribution or this Erdos distribution. And then each solution, in this case, this was the edge between this on one of the graphs, I don't remember which one. This is just to show you how each of these little mini plots are going to work. We get a box plot for the resulting solution. So at an in-group, the average degree of each person's in-group, they're sending about 2.8 ties to their own group. In that case, the weighted Erdos version for the edge between this, it did fine. And it does much better, as you would expect, as we go up and get a higher, more clustered graph. But in this particular case, edge between this did not do particularly well on the skewed distribution. So if the degree distribution was skewed, edge between this did a much poorer job than if the degree distribution was built off an Erdos random graph. So this is the detailed results. If you're interested in this, and me sending you this, it's in the slides, of course. We have a working paper on this. But as you can see, there's the first thing I want you to just notice is the amount of sheer variability in the results. Right? So all of these methods were fed the same problem, and the results were pretty dramatically different. A good fit, like the model is doing really well here. Right? That's what you want to see. So in this case, right, for the weak core networks, using the Leiden-Sweet method, you almost always get the right result. That's a good answer. We like to see that. This is a bad result. So edge between this on this graph, it's like it just does a crappy job all the way along until you get really strong signal. So the base story here is that if your network is easy to cluster, use any method you want. Like if you know your network is well clustered, whatever's fastest, grab it, it'll be fine. But in most cases, the really simple models do pretty poorly. Like the Leiden-Cox-Pox model, which I didn't describe in detail, this is a different way in which you should optimize instead of using modularity, you use a different fit score. Like it does terribly here if you just use the default. And so these are the agglomeration and divisive methods. The methods off the shelf that work really pretty well are some of the process models. And so the advantage, for example, of InfoMap does a really nice job across on this weak core model. It also does a pretty high job on these others, and it's quickly responsive to the signal, as is a few of the others. Now, as is always the case when you need some data reduction to figure out what the heck these things are actually doing, just throw it all in a regression model, right? And so this is a regression of the adjusted RAND scores, so the fit statistic for how well each method did as a function of the features in the simulation. And so this is our community signal. So this is the x-axis from those last slides. And so when the community signal is low, every method does better as the community gets better. That has to be true. That should be the case. By and large, all the models do better when you wait for in-groups that when you treat the graph as ungraded, and they do better on the normal distribution than on skewed distributions. This is bad news because the most real networks are highly skewed. Right? So a method that doesn't do particularly well on that is going to be problematic. Of the different kinds of problems that the networks do pretty well on, this double nested in different size groups, these ones end up doing pretty poorly. The hidden clusters job, they do a pretty nice job. So most of these methods are doing a pretty good job of distinguishing the true graph groups in those highly noisy set from the rest. And then of all the different methods, the Leiden modularity model, if you do the sweep, does a really nice job. The problem with the Leiden sweep method is that we cook the books here a little because, like I said, we stop when you get the best fit. And so that's making the assumption that you as a user would recognize where that is if you were looking at it. So if you don't know where to stop, like if you don't trust yourself as a user to do that sweep process, then the InfoMap or the fluid communities, these process models, do really well just off the shelf. So just pulling those models out, they do a really nice job. And those models, there's some variance in how well they do if you, instead of controlling for the different topology, you run the model separately for each topology, but the basic story is the same. So what this says is that weighting really helps. So if you have some feature of the graph that you think maps on to the social process of being in a group, include that as an edge weight. The two obvious choices in social networks are going to be reciprocity, so weight reciprocal ties heavier than non-reciprocal ties, and transitive closures. So the number of times you and I share a partner should weight our model more. So those things are weights that you can add to the graph that provide a little extra information for these heuristics to essentially get the initial sorts right. Centralized or highly skewed networks tend to be the most difficult to cluster, and it's challenging to recover clusters when there's a lot of variance in the size of the clusters in the network. Of the methods, the modularity sweep method works the best if you know that you can find the right gamma. So if you can find it and you can see where it's at, that's the way to go. With the next paper and some of the methods that John's going to show you, we'll give you some hints for how to find that. If you don't know that, then the social processes work well. The eigenvector methods work the worst, I'm stumbling on my words. And because the stochastic block models tend to be seeded with the eigenvector methods, they tend not to work any better. And so despite their theoretical sort of advantages in terms of, again, the statisticians love them, but they just don't perform well at this test. So we're in the process of, this is the first of 3 papers that we're working on. In the second part, we're investigating a little bit deeper the different ways in which you might weight edges to get some more signal. And in practice, most of these methods, if you go in and dig in the details, and you see these kinds of shelf structures in the results, and so it goes, fine, and jump. What it's doing is that the network is the method is getting stuck at too high a level. And so what it's doing is it's saying there are 4 clusters in this network, not 15 clusters. So it's finding this one, this one, this one, and this one. So the obvious solution is to embed a hierarchical structure into the clustering method itself. So you start with the first select clusters, get them out, cluster inside of that. And so if you do an actual hierarchical clustering, my guess is that most of these methods with a 2-step sort of solution where you start high and go low will give you the right solution. Now, that might be a lot more work than you need to do if Leiden will get you there anyway, but that's where we're taking it next. All right. It's not bad. Questions on community detection before we move to block models and have some coffee? So 1 and 2, please.
One question. Thanks for this, Jim. This is interesting. Is there anyone working in non-parametric base space to detect clusters?
Could you just say that one more time, please?
Is there anyone working in non-parametric base space to detect clusters?
There is a Bayesian stochastic block model that it's actually, there's a version of it that's supposed to be ready for R, and there certainly is in Python. The version that I think is available in R, it crashed last time I tried to use it, but I haven't updated. It was before I updated it hadn't updated to the 4.2 at that point. It's painfully friggin' slow. It just some of these, I'm a patient man. And so some of these models, like the Leiden sweep model is like 10 seconds an iteration, and I've got 120,000 iterations or 212 different observations, right? So I'm a patient person, but instead of seconds, it was on the order of minutes to converge on these models. And so if you're the kind of person where you have, for my purposes, it's just really hard to evaluate that. For a user who has one network they're going to work on, that's probably fine. I can take 10 minutes, I cluster it. It gets me a really good solution after 10 minutes, and then I never have to cluster it again, right? And that's fine. But if you're trying to do 100,000 of these, it's just impossible. And please.
Yeah. Do these methods assume that the data is complete? Like, to what extent it's reflecting actual clustering versus just don't have.
Yeah, so these models assume nothing other than what's given to them from the graph. So it assumes the graph is the accurate perception of the data. It's a great question about essentially what clusters would you get if you assumed random noise built into the sort of missing data structure or the nodes collected or whatever, right? Yeah, and so, so no, these models do not assume any kind of noise like that. Thomas?
Is there a sense of, or do people analyze how stable the spoofing is? Like,
Yes, so there's an entirely separate set, which you can look at the within group consistency of the solutions. And they tend to be very consistent. So each method, if it gives you the wrong solution at time 1, will give you the same wrong solution at the next time you run it. So there's a I'm trying to remember if this is true. I have to go back and look at the details. The vast majority of these models do have a stochastic seed. Edge betweenness does not. So for example, edge betweenness is the only stochastic element for edge betweenness is how it breaks tie. So it flips a coin whenever there's 2 edges that have equal edge betweenness, it flips a coin between which ones to pick. But Leiden and most of the infomap ones and a few of the others, they're stochastic in their seeds, and so they're stochastic in their end ultimately. But because of these aggregation processes, most of that stochastic noise gets chewed up by the time it reaches the final solution.
but you could probably construct an example where you have sort of 2 competing group structures, which give us, if you find them have a very similar score, and then see sort of.
Yeah, I'm sure you could, right? And so I haven't tried to make Leiden fail. So I haven't come up with a model where I've deliberately tried to trick the ones that worked. I went the other way and started saying, well, what do I think social networks look like? And so that's what these are built on. Please.
So just including choosing a community detection method, like when you're working with networks of people, is kind of like theorizing about groups of people, like how people form groups. And it just seems like the social process method is theoretically like the most substantive because you have to be, I guess, like explicit about what social process you think is going on. Okay. So I mean, with the other methods, like how this might be too big a question. Like how, like if you chose a different one, if you were someone and you were going to use stochastic block models, I mean, what?
Yeah. So if I were to, so my advice to people is if you have a social process that you actually care about substantively. So assume that I'm looking for groups that are best mapped onto the diffusion of disease, or a model that's best mapped onto peer influence, or a model that's best mapped onto status differentials, right? Then I can posit a different social process for each of those 3 models, and it might be that label propagation works best for peer influence, and something like a walk trap works best for disease diffusion, right? Because those models kind of mirror the social process that's going on. And so you might eke a little bit of advantage over using those models than you would over using Leiden. But otherwise, Leiden's probably going to be your best bet. Again, Leiden with a resolution suite. And the thing to remember is that I often work in situations where I have hundreds of networks that I'm comparing against and doing the same process over again. So having a certain amount of efficiency and having comparability is important to me. If, like most of network research, you're really doing a case study, I have 1, maybe 2 or 3 global networks, then the best bet is to do a bunch of these solutions, look at them, compare them, and see where they differ. And in fact, like all of these methods, there's a hidden assumption in all of these methods, which is that, I'm not allowed to have a marker in this room. That note is for me. But the hidden assumption of these models is that clustering is exhaustive and mutually exclusive. So every node is put in a community, and all nodes are in one community. And so in real social life, that's not the case. And so where these things, I remember who I was talking to, but where these things typically fail is where the nodes should be in multiple communities, right? So if you think back here, this guy, right? Like these nodes are together, but they can plausibly be in any of these communities, right? So a lot of the mismatches here are where you cut a line where you could just as well put the node on the other side. And so that's really a problem with the assumption of mutually exclusive exhaustive clustering when you should have something else. Please.
I guess, are stochastic block models the same or similar? How are they different from latent class analyses?
Latent class analyses are well, a latent class analysis is it's a broader class of solutions. It doesn't have to be on a network. So there's a version of a stochastic block model that is latent class analysis on a block model. But latent class analysis is a broader class of solutions.
So follow-up question to that. So if you have data that is typically would be used for like a broader latent class analyses, because if you can look at like group membership, is there, but you don't have those network pieces, could you still visualize those groups?
Oh, sure. Yeah. The beauty of this method, this is, as my students are tired of hearing me saying, I can turn anything into a network, right? And so a latent class analysis is essentially clustering on a similarity matrix. And once I have a similarity matrix, I have a network. I have a weighted network. Once I have a weighted network, I can cluster it. So, bada boom, bada bang, boom, there it is, right? So it's yes. So the short answer is yes, and that's actually where we're going next. Please.
Are there useful methods when they don't assume like mutual exclusive clusters?
Not as many as there should be, and there are two problems that need to be solved there. One is that you should have a method that says this node belongs to no clusters. It's just noise. And we do that when we do our test by just ignoring the ones that we know to be noise. So we don't, but a naive analyst wouldn't know that. So we've given that to it. And so the best solutions for that are coming out of the PCA and SVD world, where you have sets of nodes that essentially have no heavy loading. So essentially their ties are effectively random across all the different clusters of solutions. And so that's typically the best solution. The other way is that some nodes should be in multiple clusters simultaneously, and that's, I think, the most problematic, because assigning a node that's really noise to the cluster that it happens to be tied to, from a disease diffusion standpoint or whatever else, is probably the right thing to do. It's maybe not a lot of signal, it's just random luck that it's in that cluster, but it's not hurting anything really, because that's where the disease would go anyway. But for nodes that are overlapping in communities, that node's attention socially is divided between these two sets, and you'd like to have a model that does it. There was a great tool that did this. It was OSLM, O-S-L-O-M. OSLM which is a hierarchical overlapping community detection method, and it does a really nice job. And they stopped supporting it about 6 years ago, and so the code hasn't been updated. It's just not there, and so yes, there are in the literature solutions to do this. But in practice, pulling one off the shelf is hard to find. All right, one more question?
Yeah, I was also thinking a bit in parallel to latent class analysis, and I was wondering, because latent class analysis, essentially there is no definitive answer as to what kind of clusters that you would classify those observations into, but it's mostly dependent on how you would theorize it, and what are the theoretical drives or assumptions that you're trying to make. And I wonder whether coming to detection, like in terms of the process, like the optimization, is really closely related to how you're theorizing it and how you're.
Yes. So Paul Zivik was the lead author on a paper that we did, where we did a series of comparisons of these models, where we tried to figure out which cluster best mapped onto disease diffusion models. And so we had we were testing on a data set called X-Flu, so it's a data set collected at UNC, which is a bunch of kids that were stuck in a dorm for a while and they passed flu to each other. And so we mapped where that went. We didn't introduce the flu to them, but once they had it, we watched where it went. So the idea was, and so we were able to so there was a very specific process, and you were able to ask which of these models did best, and we uncovered a version that did it. If you have a different social process, you might have a different clustering. But again, the issue there is, I should back up a second. There's usually two reasons, maybe three, why you do a community detection. The first one is data reduction. You have a network of 100,000 nodes or 1 million nodes or whatever, it's too big to do anything with, and you need to chop it into pieces that are manageable. In that case, those really big giant networks, so something like our GitHub graph when we were doing a big DARPA project here a few years ago, it had something like, what was it, John, like 5 million nodes, 15 million nodes? It was ridiculous. It was absolutely insane. But the modularity on that graph was 0.98. right? And so it was already so heavily split, and all we cared about was the really big chunks, which we then dug in and did. So there, it doesn't really matter. Use the fastest method you can find. It's going to work great. If instead what you're interested in doing is uncovering like who sits together at the lunchroom by who likes each other, so really getting at the Mean Girls version of a social structure, then it really matters whether or not you put John in the right group or not. And so then you really need to dig in and pay attention to where people get assigned. And that's why I think that this consensus clustering model really is a nice model if you're patient enough to do it. Almost not because you get a new solution on top, one best solution, but because you can see what kind of nodes are ambiguous. You can then treat their ambiguity in the cluster assignment as a feature, not a bug. Right. All right, if anybody needs coffee or whatever, we'll do that. And we're going to switch over to relational block models next. Where the knots are in those pipes to mix my analogies, right? And so mix my metaphors. Can you mix an analogy? Probably not. So to mix my metaphors for pipes and strings, right? The idea is that a community is a knot in the network structure. It's a set of nodes that are tightly reconnected to each other. The positional model says that it doesn't matter so much as pipes, it matters that we have the similar perspective on the world. And so the classic example we gave is this one, right? That you have parents and kids, and it doesn't matter, right? That parents the world over are tired at 7:30 at night when their kids are cranky, right? And that doesn't matter which kids you are, right? You don't have to be tied to your kids or my kids. There's just a pain in the ass either way, right? And so the key then for this positional notion is that we want to identify a role structure. And so the collective property we get here are known as blocks. And so this is the process, instead of community detection, is known as block modeling. And this is why I have a little chip on my shoulder about the use of stochastic block model, because they stole that word from sociology and then they apply it to just a certain particular form of the block model, in which we're interested in a much more general form. And so what we're trying to do in this model is to keep the method up before I'm going to go to a little background on the theory first, but just to keep in the back of your mind what the method is. What we're going to try to do now is to find sets of nodes that occupy equivalence classes. So these are nodes that are structurally equivalent or automorphically equivalent. I'll explain what those words mean in a minute. But these are nodes that are like each other in their patterns on the graph, but they may not be tied to each other. So they're not knots in the social structure, but they're similarly patterned in the network. And so all the work is figuring out what counts as the right pattern. And so why do we care about these ideas? And so, as you might imagine, sociologists and anthropologists care deeply about role structures. And so roles are the patterned activity that we engage in socially. You know roles, you're used to them all the time, right? The beauty of roles is that roles are always implied in a sort of behavior and a rights and obligations kind of exchange. And so if you think about it, parents and children are in an exchange. Parents give love and support to children. Children give resentment and eventually love to parents, right? Cops chase robbers. Teachers have students. Lovers have lovers, right? Who's my lover's lover? Better be me, right? So my lover's lover is somebody else, there's a problem, right? And so that's what we mean when we think about roles, and every role carries with it an embedded set of social exchanges. I give something to you, you give something back to me, and those two things comprise a field and a flow of exchanges. And that flow of exchanges defines the position, right? And it's a reciprocal process. Some of these roles are well defined. So we know what cops are supposed to do, we know what teachers are supposed to do, we know what lovers are supposed to do, right? We don't necessarily know what bridges are supposed to do. Bridges is it's an amorphous role that emerges in any given network and any given set of kids, right? A class clown in one setting would be slightly different than another. We have some vague idea about what it is, right? But the kind of role you occupy may or may not have a name, but as community members, we've converged on an idea that the behavior you're engaged in is appropriate or inappropriate. And if you're doing appropriate behavior, it's probably because you're interacting, you're exchanging with your partners in a way that's accepted by the community and is appropriate for your role, right? And so what we try to do in this process is to imagine what this coherence of role systems, which is what Nadella originally argued for, is that whole societies would have stacks of roles. We'd have parents and leaders and bosses and workers and ministers, and all of these different positions would have complementary role structures. And I would do things with you, and you'd do things with me, and so forth, and the whole system would create a social system that functioned properly. Since then, we've sort of backed away from this dysfunctional model of role systems, well, still because it turns out that, well, it's a longer story, but functionalism has a series, never mind. So, in any event, we have this idea of rights and obligations with respect to other people or classes of people. Roles require this notion of a role complement, and that's what allows us to have this exchange model for doing it. The beauty about roles and role systems is that you end up having this concatenation of role ideas. And this is really clear when you think about the necessary role structures. So the common example of a necessary role structure are kinship models. And so my sister's daughter is my niece, right? My mother's son is my uncle. Right? So you can imagine what these sort of necessary relations are by the compounding of other relations. And some of the kinship is by obviously the clearest element that we have. The other element where you see this a lot is in command and control structures. So if you think about who my boss is, what's my boss's boss to me? My boss, right? And so we have this effect of which there's a chain of command, and so authority is transitive, and so that's a necessary feature. That's built into the nature of a hierarchy. But there are lots of roles that just happen to go together, right? So something like caregiver and mother are not a necessary relationship. That those two things don't have to go together. There's no logical necessity of those two. But in Western kinship societies, that tends to be the case. And grandmothers more so, and aunties yet. Aunties have a slightly different role. Like they tend to be sort of confidants for kids, but also authoritarians in certain elements, right? But not to contradict mom, but there, right? So those notions of coincidental ideas are what we're interested in finding. And so if you think about trying to find these kinds of models in networks, it's the same exact process that we're doing with community detection, but instead of doing it on the node itself, we're trying to do it, or on on this knot of relations, we're trying to do it on this pattern of ties. And so you might think there's a simpler way to do it, and it turns out there is. For many questions, right, the positional model is well answered by just looking at centrality scores. So you can go back to our discussion of centrality scores and say, well, it turns out that I want to care about bridging, and bridging is a kind of relation that is abstract and is fine for me, and betweenness centrality is all I need. If you can do something with betweenness centrality or any other centrality score, do that. It's simpler than what we're about to do. So this is just a cautionary slide to say, do centrality when you can, because the other purses end up being a little bit harder. So how do we do this? So we imagine this process, and I'm going to use this as my example. What we have here is a nice multiple relational network. And one of the beauties of, and one of the things that I think is most advantageous from a sociological standpoint of the block modeling tradition is that it natively uses multi-relational networks. And so what Jimmy was saying yesterday about how we need to bring in this sort of rich tapestry of all different types of relations, that's the idea that block modeling works with. And so the way it works is that you start by identifying some definition of equivalence, so something that makes up two nodes the same if they meet that criteria. We measure the degree to which that's true, and then we essentially develop a fit for what's there. So the standard way of doing this, the traditional way from White, Borman, and Bragger, it came out in 1976, is this thing called Concord. And what they do is they say, let's imagine some set of relations, right? In this case, we take each of the adjacency matrices for those, and we literally stack them. And so you'll notice that romance is necessarily symmetric. If I'm in a romantic relationship with you, you're in a romantic relationship with me. Feed is not. So the people I feed and the people who feed me are two separate notions. So typically you'll add both the original version and the transpose of that into the network, so you know not only who is doing it, but who is being done to in the network. And so then you end up with some k by n matrix, where k is the number of relations times the number of nodes, and then n is the number of nodes in the network, and then this becomes the thing that you calculate similarity on. And so in this case, we can see that these two nodes at the top, nodes 1 and 2, they have the same pattern of ties that is very distinct from the pattern of ties in this set. Now what Concord is I'll get to Concord in a second. So what we need to do then is define the different types of relations of equivalence. And so mathematically, there are a handful of these that are out there. Structural equivalence is the phrase that people typically use sloppily as all kinds of relations. But formally, structurally equivalent nodes are nodes that have the same ties to the exact same people. So two nodes are structurally equivalent only if they're literally tied to the same people. That's not very useful because that conflates cliques and other kinds of sort of cohesive communities with equivalence communities. And so we tend to relax that assumption. When we think about this notion of either automorphic equivalence or regular equivalence. Automorphic equivalence are you have the same pattern of ties to all others in the network. And so you can imagine these, in this case, if I remove the labels, they're indistinguishable. Right? So these nodes are automorphically equivalent in that sense. That if you just get rid of the labels, you're going to have the same set. The beauty of automorphic equivalence is that these nodes are also going to be equivalent on any summary measure of the graph. So any centrality score like degree or betweenness or centrality or whatever is going to be the same. Regular equivalence relaxes it one step more and says that the two nodes are regularly equivalent if they have the same type of ties to the same types of others. The problem is that that's a recursive definition. So what defines the same type is defined by the patterns of ties already built into the model. So you have this difficulty of figuring out how you're regular to each other. And the traditional solution to this is a series of sort of effectively random walks that's been done. It's an algorithm called REGE, R-E-G-E, that people don't use much anymore because it's also very slow, and we can do better. So most of us, So I always struggle with this because in practice, all of these definitions end up getting conflated into something we're going to call role equivalence. Because once you add a little bit of random noise to any of these, it's really hard to tell them apart. And so we're going to have a much, depending on your point of view, sloppier or relaxed version of this, which we're going to end up calling role equivalence. But a little bit of historical background. Concord was the convergence of iterated correlations. This is the algorithm invented by Borman, Bragger, and White. And they took that similarity matrix here, and they noticed something interesting to it. They said one way to get its similarity would be to take that whole thing, and instead of having zeros and ones, which I just made up in this case, just start with the correlation matrix, right? So stack your network, build the correlation matrix, and you can see how correlated people's ties are with each other. And I thought, well, that's interesting. That gets me so far. What happens if I correlate that? Right, so we take that, we correlate that again, and again, and again, and before you know it, it's going to converge on either all positive ones or all negative ones, which is kind of a fun feature, and you get a single split. And this is my font got messed up. I don't know why that's supposed to be in the middle there, but it's really frustrating because this is clearly a device-dependent font feature, which I didn't know happened. So anyway, if you could look a little better, you'll see that here are all positive ones, here are all negative ones. And what that does is that gives you this splitting structure. And that splitting structure will say, given the whole graph, every graph when it starts can be split into two pieces and two pieces and two pieces. And this does a remarkably nice job, if you know when to cut it at the end, of getting at intuitive notions of structurally equivalent nodes, or role equivalent nodes. This is an example that Peter Mook and I put together a few years ago where we were trying to look at co-voting in the Senate. And it turns out that the problem with voting in the Senate is that it's a really dense, kind of ugly graph. It's hard to make a whole lot of sense of. So what we thought was, well, maybe we could simplify this graph by looking at structurally equivalent positions. And so we did just that. And so we applied Concord to this graph and then identified sets of nodes that are in this, that have are in a similar position. And these nodes, as you might imagine, map onto the things you would expect, right? And so you end up with nodes that are party loyalists and nodes that fit between groups. And if you go and look at this over time, you can see that throughout history, this is from 1910 here to it's like 1912 or 1912 when we did this. You end up, 2012, sorry. You end up with every party, almost definitionally, you're going to have party loyalists. And the people in this position, right, they just vote the majority party line. But historically, or at least for the last, between 1910 and 1990, it was possible to have some set of leaders in the Senate that could occupy the middle position. And this middle position of being, bipartisan, to more or less degree, allowed the party loyalists to do the things that parties are supposed to do, but it allowed the Senate as a whole to function because you could have these kinds of bridges to get majority measures at time to time. Now, over the course of history, right, you'd find some periods where the party loyalists would split, and so you'd end up with some, true Republicans and sort of, rhino Republicans, to use today's language. And you'd see the same thing on the Democratic side, right? You'd see this kind of part through. But historically, and the y-axis here is the mirror of the modularity score for this solution. What you see is that the polarization has just gone off the scale. But what's nice about this is that we've gone from you're able to display a graph now that is, instead of being 100 nodes, is just really like about a dozen nodes in any given wave, because these nodes are effectively equivalent. And by moving them away, you can focus on the thing that's there. So that's an application of structural equivalence to this case. Now, one of the problems with Concore, there's lots of problems with Concore. It's an ad hoc method. There's no real theory behind it. It turns out that it's very closely related once you dig into the way that correlations are built and the way that iterations of correlations are built, is that it's effectively a poor man's versions of an SVD, and so it ends up being perhaps not the best overall. While remarkably robust, it's not the most sort of elegant model. Ron Burt had a different model. Ron Burt came up with this idea of detecting role equivalence by using triads. And so now you get to finally see my favorite element of social networks, which I refer to this as the periodic table of social elements. This is the triad census. And the reason I refer to it as the periodic table of social elements is that any social behavior, like remember we care about role behavior, any social behavior is fundamentally a behavior of one person to another with respect to a third. And so it's you and me and the audience, right? So that's the way, and where every other person in the network becomes the audience. And so in some cases, right, it's you and me all day. We don't care about anyone else. This is the romance triad, right? Like we better be here. This is the unrequited love triad, right? Or the stalker triad, depending on where you're at. But the notion is that if I have a social theory, I can map it on to a group of three. And honestly, in most cases, a group of 4, 5, or 6 is just a concatenation of multiple groups of 3. This is what Zimmel meant when he said the move from 2 to 3 is significant. The move from 3 or more is kind of, more of the same. And so, for example, if I care about my social theory as a friend of a friend is a friend, then it ought to be the case that a friend of a friend is my friend. Right? And that's the case here. A friend of a friend is a friend, and so forth. And so you might have these versions of transitivity. I might have other kinds of things like hierarchical agreement, that if two people are friends with each other, they agree on the status of thirds, right? It might be that reciprocity is a rule, and these things could all be happening simultaneously. So whatever social process you care about, you can map onto the expected distributions of triads. And this font thing is just killing me. That was a beautiful straight line in the original PowerPoint. But in any event, you can think about the distribution of triads in the network as a way of summarizing the aggregate expectations of what people did with respect to whatever rule you had on the social behaviors. And so we can go through and think about how people are embedded within these triads. And this was Ron Burt's insight. He said, let's take the triad census, which lets us see what each motif is, what you'd expect in a network or not, and then ask how people are engaged more or less frequently in that setting. So if I'm a social isolate, I'm going to be in this situation a lot more than I'll be in any other situation. If I'm a social butterfly, I'm going to be over here all the time. And you can imagine in this case, for a network of 16, there's 16 isomorphic triads in any directed graph, or classes of triads. Within those 16 isomorphic classes, there are 36 different positions. That is, the blue dots here. So there's in the 102 triad, There's a reciprocal, you're either the member of the reciprocal dyad or you're the isolate. In this case, you're either the end of the reciprocal tie, you're the bridge, or you're the target, right? So each node has occupies in any given observed triad in the network. You have some occupation, sort of which some element which you're in it. Sorry, I did not say that sentence well. So let's just give a quick example. I think this will make it a little bit clearer. This is just killing me. I should have. I didn't. Is that what happened? It's just killing me.
Yeah, they do.
Boy, they clearly do. Well, I'm never going to get these. I'm not going to. Screw it. All right. I'll just ignore it. Ignore it. So the point, of course, is supposed to be that what you could see here, if I'd done it right, is that A and B, they out of all these 36 triads they could be part of, they're the same. So they have the same distribution across. So 36 times they're in the first one, 20 they're in this position, and so it's counting the number of times they're in each of those positions. And so each person in any given network, each node, is going to have a vector that's 36 elements long, and it's going to have some frequency of the amount of times you occupy one of those or not. And then you can just count up how similar we are with respect to those vectors. So effectively what you've done, for those of you that are thinking about today's sort of language and large language models, is you've come up with a node embeddedness score. You said that I've turned the node network into this 36 element vector. And that vector then summarizes the pattern of ties I have to every other node in the network. That's kind of cool, right? Because you have this ability to take a network of, no matter how big it is, each person's summary of their involvement in that network is just 36 elements long. Right? And that gets you in all my local equivalencies. It tells me how similar I am with respect to you, me, and a third for all possible thirds in the network across all things. And so if you take that sort of vector and cluster it, you get people who have the same pattern of ties. And so you could do it, there's 36, the vector is 36 elements long if you have one relation. If you really want to do compound relations like sex and drugs, then the number of possible positions is much larger. But it turns out in practice, you can just put the two vectors next to each other. So I have two 36 element vectors, and usually that gets you where you want. If there's a lot of weirdnesses in your graph, you might have a third one, which is sex, drugs, and joint. And so you end up, instead of having to deal with the actual compounding of relations, you can just think about the compounding of the vectors, which does a nice job. But in that case, you end up with a really nice summary of the network. So in this case, there's 3 levels to this hierarchy, and they pop out quite nicely from the element. So what does this look like in a real graph? This is a small, just so you can see it, what a small high school network looks like. I think this might actually be a junior high and high school combination. So a really small rural school in eastern Pennsylvania. And in this case, we're trying to figure out which kids are which. And so symmetric ties are in orange, and directed ties are in black. And the directed ties have the arrows so you can see where they go. And if you apply this process to that network, you can go through and say, well, where is the spot that I would cluster this network? Well, I just end up using a hierarchical clustering model where I then pick the solution that has the highest modularity on the similarity matrix. So I calculate this similarity matrix that looks like this. I treat it like a weighted network, and then I cluster it using a simple hierarchical clustering, and the point at which I would maximize the in-group similarity is where I cut the graph. And in this case, you ended up with 7 unique positions in the network. Now, the key element of this is that positions may not be communities. So in this case, you'll notice the pink position, right? These nodes are not necessarily tied to each other. The green, this sort of lime green position is tied to each other. So a position can be a clique, but it need not be a clique or community. So this is what this one ends up looking like. Right, and so you end up with these 7 different positions, and this is the mixing matrix of those positions. One of the things that is the classic hallmark of traditional block modeling is that you take your large network and you turn it into what's known as an image network. And so in this case, we have the 7 position, and this is known as a self loop. And so 7, the members of group 7 tend to send ties to themselves. Members of group 3 tend to send ties to group 7. Group 1 is on the outside. So that's how you read these image graphs. And the layout here is by hand. You sort of figure it out to find a way that sort of makes sense of it. But you can see the same thing here, right? So if you look at the mixing matrix, you can see that the odds of 7 being tied to 7 is about 8.5 times higher than you'd expect by chance, whereas 4, for example, is about 7 times more likely by chance. But group 3 here, they don't send any ties to themselves, or very few ties to themselves. So that's the way you read this process. And the little element here up the side is just giving you, for each of those 36 elements in the triad census, the position census, I'm giving you a difference from expected value in this set. So the hallmark of position 1, so these isolates, is that they are essentially really overrepresented as the isolated position in the network. So everyone else is there, but they're not. Whereas position 7, they have a lot of these deeply embedded ties, and they're the target of other ties that are built in there. So you can see that that's the kind of position this is, that this is a popular clique. Whereas position 5, these folks, you notice that they tend to be popular, or they tend to be, outsiders. They're nominating other people who aren't reciprocating them. And so they are kind of wannabes in the sense that they would like to be members of this group, but they're not. So you don't get the reciprocal return tie on that. And so if you're doing if you're doing a case study, you have one study of a school or a community or a town or whatever, then you can do this. You can just go through by hand and sort of make sense of what these positions are. If you're doing it in a large setting with lots of different schools, you need some way to automate this. And in the book, if you haven't got the book yet, grab it. We talk about ways to do that. I'm not going to go through it in deep detail here, but if you do it effectively, what I do is a second order clustering. I cluster the clusters. And when we do that for the all prosperous schools, which is 360 odd schools across eastern Pennsylvania and Iowa, you get these handful of about 8 different positions that are kind of fun to think about. The first one are these uninvolved outsiders. So this is a common position in schools. These are your social isolates. These are the kids that just really aren't involved in much. And if you look at their centrality scores, they tend to be lower than expected in degree. No one likes them. And people they do like, they tend not to be reciprocated on. So it's a sad position to be in. There's this group that we refer to as the aloof elites. These are people that get nominated, but they just don't nominate anybody else, right? So they have very high in degree. You'd expect they get nominated more often than you'd want to. If you ignore the direction of the graph, they're in the middle of it, so the people who are nominating them are also popular, but they don't send any ties, right? It's probably because they were blowing off our survey, right? These would be my guess. But the position that they occupy, that pattern that they occupy is well represented in that set. Just a little ex post sort of evaluation of what these features are. The patterns that emerge fit nicely into 2 by 2 by 2, which is, those of you who've taken my classes know that everything in the world is a 2 by 2. So this is an advantage for me because I now have an extra dimension that I've put it on. But you can think about the number of ties that people sent or the volume they have, which is either high or low. You can think about the intimacy of the tie or the reciprocity, it's either high or low. And then you can think about the respect you receive from outsiders, so the hierarchical setting in the network. And on the outside, you end up with these sort of popular loners. These are people that are getting nominated by other people, but they're not being nominated by anyone else. And you go through the set of the way our solutions found, and they map on nicely to all of these sets. So we get some people that are out in the outside and so forth. I guess I have time to go through a couple of these. But what's nice about this way of thinking about it is that it helped us to think about not just the positions we identified, but sort of what it meant to be in this position in the school. So if you have really dense reciprocal ties, so you have, everyone likes you, so you're at the top of the hierarchy, you have very high reciprocity, and you have lots of ties. That's a classic Coleman leading crowd. So these are the kids that are, these are the mean girls in school, right? This is the kids that everyone likes, they like each other, and they sort of lord it over everyone else. And so that's the world they're set in. And whereas these folks that have relatively high volume, they want to be involved in the world, people like them, but people don't reciprocate the tie back, those are your lieutenants, right? Those are the people who want to be a member of the elite, but they're not quite there yet. And so you can think about this, and I have a status model in my head coming out of Coleman, which I think maps on nicely to what schools are like, and it seems to fit well in this setting. A little bit of things that's kind of interesting about being in these positions is that if you think about each of these positions, they don't rank nicely, but I've tried to rank them from essentially your leading crowd to your outsiders. With we can debate whether I got the order right in this set, but you can ask, well, if you're looking at this being in these positions over time, because these are dynamic networks, it turns out that women are much less likely to leave the leading crowd position. So if they're in it, you'll see that so these are statistically significant as bold, and red means that you have a less likelihood of doing it. So if you're in the leading crowd, you stay there. If you're anywhere else in the network, you're likely to arrive at this federated friends model. So women are more like, girls in this case, are more likely from any other position, this is a mobility matrix, are more likely to come to, as the odds ratio is higher than 1, they're more likely to come to the federated friends position. But if they're in the leading crowd position, they tend to stay there. So that's kind of an interesting, I'm sort of finding on that set. Poor kids, that is kids who receive school lunch, if they're in the outsider position, they tend to stay there. That's the bottom row, so they don't tend to leave that position. And if they're any other position, they tend to arrive to either from, like, for example, they have 3 times the odds of moving from the lieutenant position to the outsider, or from the leading crowd to the popular loner position. So they're likely to move out of that. So it suggests that being poor in these settings leads to status instability and lower status mobility. Deviant kids, they have kind of an interesting pattern. There's maybe 5. I'll leave that joke aside. But there's if there's any evidence here, if this isn't just random noise, it seems to be the case that deviant kids are somewhat more likely to move from somewhat peripheral positions to central positions. And so this is a very rare cell, so you don't put a whole lot of weight on it. But kids moving from the outside to the leading crowd, like deviant kids are more likely to do that than others that start conditional on being outsiders to start with, or to move into the periphery of the leading crowd, so that's what that is. Those that are in segmented friends, they're somewhat more likely to become more popular over time, and those who are in those tight federated friend groups are somewhat likely to move their status up to either the aloofs or the leading crowd. So that means the deviant kids are likely to move into popular positions, I'll get you in just a second, but so are really good students. And so school systems have this kind of interesting dual process system where you get to be popular either by doing bad stuff or by doing really good stuff. So you either become teacher's pet or you become the rebel, but either case will get you into the leading spot. Raquel? We measured deviance with a scale. It was a self-reported questionnaire for the amount of drinking they did they lie to their parents, did they cheat on a test, I can't remember all the exact items, but it's minor delinquents. So it's all self-reported, right? Yes. So it's and I think I did the same thing with smoking, but so there's some substance use effects there. I don't think it was in that particular measure, but that's the idea. Please.
Is there any evidence that people are inflating those responses to these self-reported deviants to be perceived as cool while you're collecting information?
No. But I'm answering your exact question. There's no evidence for that. But we also haven't looked for any evidence of that because I don't know how we would, right? So all the associations are consistent with reasonably honest responses. They're anonymous surveys, that kind of thing. And they certainly have no reason to impress us, right? So we're not there. And so we suspect that they're telling the truth, but it's all self-reported.
I'm just reflecting on being part of a small class and remembering people come in and having responses for at the time their evaluation things, and because we all took it in a room and we knew everyone in that room, no one took it seriously, and all of them, we definitely skewed someone's data.
Yeah.
In hindsight.
Yeah, it's one of the things that some other work we've done is that, which is focused just on popularity, not on this cluster version of popularity, that it turns out that there's this, I'll never find the figure, but there's a really interesting saddle shape between deviance and change in popularity. That at the baseline, if your popularity hasn't changed at all, kids that become more popular, the more deviant, the more smoking and drinking they're doing. And so, but then if you're losing popularity, you engage in that activity even more. And so there seems to be some sense in which kids recognize that they gain status through adultifying behaviors, and if they're losing status, they engage in it a little bit more to gain it back. That's at least the story we tell ourselves from the data we can see. In any event, there's a lot of ways you can do these kinds of things. I think it's, I would argue that one of the richest elements in social network analysis is this positional modeling, multiple relational networks to look at different types of people across different role sets. We kind of got just, I shouldn't say this, the field really invested heavily in connectionist models for very good reasons, for peer influence reasons, for the spread of disease, for all kinds of features. And so we're really good now at connectionist models. We know we have good flow models, we have good predictors of ties, which we're going to talk about ad nauseum tomorrow, right? But we kind of let this side of the world, this case study, this positional model about thinking about types of people in a community and the ways in which the community generates roles and systems to the side. We left it to the ethnographers, and they did a great job with it, but we kind of want it back. Or I want us to take it back. I want you to take it back. I think there's a lot that can be done there to really learn about the ways in which people engage with each other and with the health system. So if you think about, this is a social network and health workshop, much of what people are doing in terms of their own self-care is a reflection of their position in the society and where they think they fit. And we can model where they fit by virtue of these kinds of techniques to figure out what type of a person they are in terms of the relational pattern with others. And my guess is that some types of people are going to respond to certain kinds of health messages differently than others, and being able to identify that would probably at least gain some advantage to thinking about things like vaccines, things like preventative care, things like being shut in and lonely, like all kinds of features that we could sort of deal with in a way that is much more holistic and community-driven, that we can, but nonetheless rigorous in a way that I think could be a lot of fun. And again, I think it's one of the promises of network research that we really left to the side. So I sort of hope you pick that up. I'm going to know you first, and then you, please.
It's like even with this example of high schools, like when you map that, you mentioned ethnography and like mapping it onto qualitative interviews and stuff, like do those kind of empirical things match?
The problem is the people who collect masses of quantitative data don't do ethnographies and vice versa. So I don't know. I hope so. But I think that's a wonderful area of work, and thankfully, qualitative network analysis is on the rise. So there's every year for the last 10 years now, there's been a full track at the Insta Sunbelt meetings devoted to qualitative network analysis. So there are people that are doing it. There aren't as many people doing it jointly with full-scale qualitative analysis to do the mapping on it, but I think it'd be great to do. Please.
So what I immediately thought of in this, and I'm just curious to what extent you do this, is that, so I'm thinking about it from a provider network, gatekeeping in healthcare systems. I'm in mental health, so there's a lot of gatekeeping in mental health. But that really position and connectivity are really both relevant, and people occupy positions that are critical to connection.
Mm-hmm.
So are there ways that people integrate those two perspectives? Because they've been presented really separate.
That's a very fair point, and I think I've made the case deliberately hard in order to, or stark in order to make it clear. But it is the case that your position, it can be defined by your connectivity. So a bridge as a position is a position that's defined by your ability to connect otherwise disconnected folks. The point is that the behavior of the bridge isn't driven by the fact that they're connecting these others, or isn't. Two bridges are similar not because they connect the same people, but because they're both connectors. Right. And that's the feature. But absolutely. So the fact that and I think what you're pointing out is that in something like the healthcare, their bridges, their connectivity is linking patients to services, right? And so by virtue of the constraints that they face, the healthcare moderators and guides and so forth have the same set of constraints in different hospitals, right? It's the position that matters, but it's a position defined by the flow of goods in the rest of the network.
It's also information being shared. not just
Between,
patients. Yeah.
yeah.
Provider information
Yeah.
and exchange team-based work.
So yeah, it's perfectly reasonable. Yes, yes, you can certainly do both. Absolutely. Please.
You mentioned how waiting it helps a lot with community detection precision. To which extent is there an effort to incorporate waiting into triadic analysis in the
We don't know yet. The triadic motifs definitionally are not valued, and so it's either a transitive triad or a not transitive triad. You could have versions of these that would be you could essentially say the extent to which the weighting of this triad is transitive. So transitivity is something that actually is akin. It works well for weighting because it could be A is greater than B and B is greater than C, so A has to be at least as big as B. That kind of stuff. You can do those kinds of sentences. It's harder to do for a few of the other patterns, but you could do it. No one to my knowledge has done that. The beauty is that really all you need for any of the, like I use it, like the triadic model is great because it does a nice job of summarizing these other features. But at the end of the day, what we're actually calculating here is something very similar to a version of automorphic equivalence. And the thing that's nice about, where the hell did that sentence go? There we go. The thing about automorphic equivalence is that it really, all it turns on is that each node has comparable properties. So you don't have to do the triad part. You could calculate 100 of your favorite centrality scores. And so two nodes that have the same centrality scores across a lot of different centrality scores should be the same. And so there's a whole series of, there's a fairly new field now of node embedding and motif embedding in networks, which is exactly like word embedding. So it's exactly like the work coming out of large language models, but done towards graph theoretic motifs. And so that world should be able to handle value networks, so I haven't dug into it enough to know for certain. Ben, you had a question.
So, kind of goes back to health. So have you seen anyone do work relating structural, any kind of equivalence rather, back to similarities in health outcomes? So you would think
Only very roughly. The one you see most commonly is isolate or not, right? And so being an isolate is a position, and isolates tend to be, what's that?
One is the loneliest.
There you go. So you end up, so that, but otherwise I haven't seen hardly any of this kind of work done on a general sense.
the only thing I've seen along those lines is that partners and spouses seem to have similar outcomes, like tend to die in rapid succession. And that might be, partly about structural, some kind of equivalence.
Yeah.
But I would expect that blocks of people who are in similar blocks have similar health outcomes. That's going to be a fascinating.
It feels like it has to be true. And let me give you a simple example. In modern sort of industrialized societies, our occupation is pretty good proxy for our position in a block model. And the fact that there's occupational differences in health outcomes are probably because we're differentially exposed to health threats. And so, but the reason bus drivers got COVID is because it's not because a bus driver caught it from another bus driver. It's because bus drivers are exposed to lots of you jerks out there who are sneezing on them, right? And so I think it's that feature of being a bus driver which is capturing, in this case, a disease-relevant position, which would be likelihood of exposure to lots of folks. Tom?
I can't remember if I asked this question last year, but
Then I can't remember if I answered it last year.
I know I've tried, and in the process of building up the world truth for idea, I've tried it on different data, and sometimes, one thing I like about the tools is now saves a lot of time to test ideas that don't pan out, right? I find sometimes when you're doing role analysis, it seems like there should be some best practices for checking data to see if it's viable for this kind of thing. I I think in past attempts I've struggled with like, especially with multi-relational networks, like maybe the network of a certain type of tie like isn't sufficiently dense that like really you should just be doing a binary coding, right? Like kind of this isolate as distinction. Similarly, right, if you end up discovering that like two types of relations are like pretty closely correlated, right? And so like including that in there. I don't know, do you have any like data cleaning in the way that we would recommend for like crosstabs?
Yeah, I mean, not really. I do think that most of this, so I think you mentioned it pretty quickly there. There's some, like the obvious position is isolate or not. And so isolates, I mean, you kind of have to put them off in their own world, just because if you're not connected to anything else, there's no more juice to squeeze from that lemon. So you just got to like put them on the side. And then I think the correlation across different relations is a good indicator of whether or not you should combine them. The feature is most of the time we don't have a dozen relations, and so it's like if you only have 3 relations, you may as well use all 3 of them. But like I'm involved in some projects out of the UCSF where we have data from fishermen in Lake Victoria, and there you have 7 different relations amongst a group of fishermen. And we've looked at the correlation amongst those relationships, and it makes sense to collapse a few of them. So the other thing that people have done is they've reported it as data quality, but I would love to see some work figuring out what's really going on, is relationships that should be sort of mirrors of each other that might not be. So if I loan you money, I would hope that you would report that I loaned you money, right? Or that you borrowed money from me, but those two tend not to be complements of each other as much as you might expect. And so figuring out when that's true or not would be an interesting feature. But as far as data, parsing out whether that's a data cleaning issue versus a data, a substantive issue is going to be case by case.
Like one example, I think it was like the like sanctioning the rehab community stuff, right? Just broad strokes for everyone. Like it's a network of people in a community, whether they're like praising or punishing each other, right? And I found, granted, these were like very fine-grained data, right, from dynamics, so it was already kind of tricky. But one thing I found was that in a lot of cases, the people who were praising were the people who weren't punishing, and there's a case where you have a strong negative correlation. And the clustering kind of fell apart because all it really did was partition on like levels of activity of praising or punishing. And that's the case for like, it's not that you have such a clear correlation that you want to combine, it's that the correlation is so strong that it really, like the partition just happens on one type of tie or the other, and it's just kind of a dead end there. And I think that's also a weird case to look at.
I mean, I think this whole field is just ripe for both methods and substance work. So that's why I get to give this talk every year, is that I want you to do this. I'm a prophet in that. I'm what's the word? Proselytizing to make this work. Evangelist. Thank you. That's the word I need. All right. We're going to switch over for a minute and then get a little how-to coming from John. And then after John, Ashton's going to tell us about compound relations for kinship networks. So, John, the floor is yours.